Fleming's right-hand rule. Fleming's right-hand rule is used to determine the direction of the induced current flow. So for example, if we have a conducting rod moving in this direction, and it cuts across the magnetic field lines which are perpendicular to it, and using the Fleming's right-hand rule, aligning the thumb to V and your first finger to B, we will be able to conclude that the induced current will flow in this direction. And in order to calculate the induced EMF, we'll be using Faraday's law, focusing on the magnitude of the induced EMF. So in this case, it will be a change in magnetic flux linkage divided by the change in time. And over a course of delta t, we can assume the distance traveled by the rod to be delta x. So the magnetic flux linkage will be BA, where A in this case will be the length of the conducting rod multiplied by delta x. This is the area that the rod has swept across. And substituting this expression to the change in magnetic flux linkage, we will be able to derive the expression where the magnitude of the induced EMF is equal to BLV, where V is the velocity at which the conducting rod moves, and it is important to note that B has to be perpendicular to V in the application of this formula. So let's now take a look at an electromagnetic flow meter. In the electromagnetic flow meter, we actually have a conducting fluid. In this case, a conducting liquid flowing in this direction, V. The magnetic field is directed into the plane of the paper. So you can label that with a cross to indicate the magnetic field going into the paper. And using the Fleming's right-hand rule, you are able to conclude that the induced current will flow from Q towards P. So the next question we're going to discuss is that which electrode is at a higher potential. To do that, we have two methods that we could use. Let us take a look at the first method first, which is actually a continuation of what we discussed earlier about using the Fleming's right-hand rule. So the B field is as indicated here. This is the direction of the flow of the conducting liquid, and that is the direction at which the induced current is flowing. It is important to note that we now will treat PQ as an EMF source. And if PQ is an EMF source, the current will now be exiting from the plate P. So there will be a current that will be flowing up. And the conventional current will then flow through the galvanometer, enabling the galvanometer to be deflected as shown. And the current will return back to plate Q. So with that, PQ is now an EMF source where the current exits from plate P and returns from Q. And hence, because of this, the potential at P will be higher than Q. It is important to note that internally, the induced current flows from Q to P. Alternatively, in the second method, we'll be using the Fleming's left-hand rule. In this case, we will be studying the electromagnetic force acting on the electron. So if we have an electron that's moving from left to right in this direction because of the motion of the conducting fluid, we know that the conventional current flow will be in the opposite direction. So this is the direction of the current. And the magnetic field continues to go into the paper. With that, using Fleming's left-hand rule, we know that the electrons would be exerted with an electromagnetic force that will be acted towards Q. So the electrons will then move towards plate Q, and from then the electrons could actually be flowing into the external circuit X drawn. And if the electron were to flow in this direction, then we know that Q will be the negative terminal of an EMF source, while P will be the positive terminal of the EMF source, therefore allowing us to conclude that the potential of point P is still higher than that of Q. Let's now take a look at another example of an electromagnetic flow meter. In this case, the fluid is flowing in this direction, and you have an external power supply that provides electrical current flowing into a solenoid, which then provides a vertically downwards magnetic field. And with that, we could actually use the Fleming's right-hand rule to conclude that the induced current is flowing in this direction. To be better able to derive the induced current flow, let's take a look at the plan view if you were to look right from the top. So in this case, we actually have the tube. This will be a point X. The point Y will be on the adjacent side. We have the direction of the fluid flow in this direction. The B field acts into the paper, and using your Fleming's right-hand rule, you will be able to then conclude that the induced current flow will flow from Y to X. And based on earlier discussion, it is important to note that this is the induced current flow within the XY, and we are treating XY as an EMF source. And with that, we will be able to conclude that X has a higher potential. So what we have described earlier utilizes method 1, that XY is treated as an EMF source, and we use Fleming's right-hand rule. As earlier concluded, that the induced current flow internally will be flowing from Y towards X, and hence the current flow will exit at X and will flows back into Y. So with that, the potential of X is higher than Y. We could also use an alternative method whereby we look at the electron in the conducting fluid, which in this case is moving in this direction. So based on understanding of conventional current flow, the electron flow is directly opposite of conventional current flow, which means the conventional current flow will be indicated in this direction as such. Your B field will be acting downwards. And using Fleming's now left-hand rule, the magnetic force acting on the electrons will be towards Y. And with that, the electrons will then exit and returns towards Y. So with that, we can conclude that Y is the negative terminal of the EMF source, while X is the positive terminal. So the conclusion is the same. We will still arrive at the potential of X higher than Y. This is another example that we look at. We have a conducting rod rolling down parallel conducting rails in the presence of a magnetic field that's acting downwards. So the first thing that we do is to determine the direction of your induced current flow. So in this case, with using the Fleming's right-hand rule, we can conclude that the induced current will flow from X to Y. And with the induced current flowing from X to Y, using Fleming's left-hand rule, with the induced current flow, we know there's an opposing magnetic force acting on the rod, opposing the motion of the rod. In this case, the direction of the magnetic force is upslope, while as a consequence of its weight, there will be a force acting downslope, mg sine theta. So in order for terminal velocity to be reached, Fb will be equal to mg sine theta. And in order to prove that the terminal velocity of the rod is this expression, the first step that we need to do is to calculate the induced EMF, which in this case is this expression. And using the induced EMF to be equal to current multiplied by R, we're able to find an expression for the current, where R in this case is the resistance of the slides. And finally, we will use F equal to BIL, and mindful that we will only use the component of B which is perpendicular to I, the current, which is equal to mg sine theta, and that is the component of the weight that's acting downslope. And substituting current with this expression, we will be able to work out that the terminal velocity is equal to this.